first of all, it's a great pleasure to be here today. Thank you very much. And maybe to give you some background, I'm a hardware engineer, so this presentation obviously will focus a little bit more on the hardware aspect of things. Before we dive into the actual topic, I would like to take a minute and introduce Miromico. For those who do not know Miromico yet, we're an engineering company located at the very heart of Zurich. Around 40 engineers which work in the fields of embedded systems and integrated circuit design. With around 20 years of experience, we gained a lot of experience in the fast and flexible development of Internet of Things devices. We're particularly well known for our LoRaWAN devices. Of course, as an engineering electronics consulting company, it's our mission to make your business idea become real, starting maybe just from a simple proof of concept, but really up to large-scale manufacturing and deployment. Miromico also has its own product portfolio, which includes wireless modules, gateways, and end nodes such as sensors. Then, last but not least, we also do offer manufacturing as a service. Maybe not all of you are that familiar with that term. That basically means you outsource the whole production process to us, which also includes supply chain. As many of you probably know, that's particularly hot and spicy topic nowadays. And we actually do have capabilities to produce at least 250K devices a year. Now let's have a little look at our product portfolio. On the left-hand side, you can see some examples of our wireless modules. We offer different wireless technologies, of course, LoRaWAN modules in sub-gigahertz, 2.4 gigahertz, but also different wireless technologies such as Wi-Fi, Bluetooth, and IoT. Miromico also has its own line of gateways, the Miro Edge, which comes in indoor and outdoor variants. We also have a selection of end nodes, such as IRQ sensors, smart buttons, trackers, and many more. Now, if we have a look at the Internet of Things ecosystems, most people usually think about the end devices because often that's the closest related to your business case. Of course, for Miromico, the gateways are also very, very important because that basically is the bridge between your end devices and your cloud. During this presentation, I would really like to focus on the left-hand side of this visualization, the embedded systems, namely the end devices and the gateways. Now, today's topic is cybersecurity, so one naturally thinks about cyber attacks which are performed on a device without having physical access to a device. However, with nowadays many devices being deployed, maybe outside, maybe in public spaces, it's also equally as important to protect your devices from actual physical tampering, because that might actually be the weakest point in your cybersecurity concept. A protection of the hardware starts at the very silicon level. But before we dive into that, I would like to give you some foundation by giving a little recap on how a modern wireless communication standard such as LoRaWAN implements already a base security which can already help to protect yourself against a lot of passive attacks. The LoRaWAN security standard is basically all revolves around the principles of encryption and authentication. That means that only authorized parties can join the network and only authorized parties can send up and down links. And it also means that the payload is encrypted at all times. In the case of LoRaWAN, this is actually implemented by the means of 228-bit AES keys, which on one hand are stored on the end device, and the other hand, they will be located on the join server. This usually happens while you register your device. Now, as you can see, this already protects you as these keys are never propagated through the actual network, and you also have some dynamically created keys. This already protects you from many passive attacks. However, it does not protect you from the theft of your keys. As soon as you have the keys, you're basically lost. Coming to that, I would like to stress on how important it is to protect your device's identity. That might sound a bit naive, but I held so many IoT devices in my hands, which actually didn't even encrypt or protect their flash, and the passwords were just really easily extractable. Another thing is, of course, your debug port is very handy, but please, before deployment, close it, or ideally do a factory programming and don't include a debug port at all. Of course, there are also way more sophisticated ways of stealing device identity, so-called side channel attacks, which basically make use of the intrinsic properties of hardware, such as power consumption or electromagnetic radiation, in order to extract some valuable information. Another weak point of systems is that many devices just come with the pre-shipped factory bootloader. Well, that comes in handy and doesn't cost you anything, but think about that. That bootloader can boot anything that was compiled properly for the given device. Means also unauthorized parties can boot on your device, maybe worst case even over the air. This can make your IoT device part of a botnet. Then, last but not least, hardware can also be very vulnerable to more sophisticated attacks. One example would be supply tampering, where you slightly modify the power supply or you manipulate the clock signal. This can lead to a malfunction of the device. For example, it might jump over a few lines of instructions, potentially circumventing some security measures. If we have a look at impacts, of course, different attacks, different companies, different impacts. That might be a denial of service attacks. A complete service goes offline, you get blackmailed, or you abuse sensitive data, maybe medical data, maybe financial data. In the end, this all boils down to a loss of money, but especially for us being a consulting company, also a loss of trust, and in the worst case, a loss of customers. In order to understand on how to properly design highly secure devices, I would like to present that metric. This is not a Miromico thing, that was actually established by the Microsoft Research Group. And I do not want to go into great detail here. However, I have two big take-home messages from these 7 properties. The first one is that the very root, the base of the pyramid, starts at the silicon level. If the silicon level is not secure, then your operating system or your cloud service might be broken just by tampering with the hardware. The other important message is, if you really want to design a highly secure device, you need an end-to-end solution, starting at the silicon level. On top of that, you might want a proper secure operating system, not just a bare metal application, and of course, the cloud service. Now that we know that the real root of security is the silicon level, I would like to give you an overview of certain solutions that you can use to protect your hardware. Of course, there are many attacks. It's impossible to summarize all of them within this keynote, but I would like to give you some hints. First of all, we have talked about how bad it is if your firmware is tampered with. For example, having a malicious firmware booting from your system. What one usually implements is a so-called secure boot. That means you have an authentication key, usually an asymmetric key pair, which then, of course, needs to be stored in a secure element, something like an eFuse one-time programmable memory. This way, whenever an image is compiled, it needs to be signed with that actual key, and then on the exact moment of boot, the system will verify that this image is coming from an authorized party. The same is valid for secret recovery. As we said before, never store your key on an exposed piece of memory. Also be aware that probably the best is to have a compact solution, a system on a chip, because one also needs to be aware that open signal lines, for example, I2C, especially if they're routed on the top layer, maybe you even have some BIOS there that you can scratch, and of course, test points, they can be a very easy target for attackers. Then against active probing, JTAG violation, and reverse engineering, of course, there is the option to implement the secure JTAG, or to close the debug port completely, maybe not having a debug port. Another way is so-called camouflaging, which on one hand means you design your hardware in a considerate way. As I said, you might route very sensitive circuitry through middle layers, maybe even using microvias to have the least exposed surface. But on the other hand, it can also mean that you use dummy signals to confuse the attacker. Against physical hardware modification, that's a tricky part, and for some attacks you might almost not be able to identify. Of course, there are mechanical solutions. Unfortunately, usually these mechanical solutions are implemented, you open the device and everything breaks. That's not very sustainable. Of course, you can have some fault detection, like control signals, that when the control signal is missing, you know a piece of circuitry was removed or tampered with. And then there is also the so-called active shield, which basically is a mesh that, like a sensor that you will put over the sensitive circuitry that will detect any kind of modification. Memory attacks, of course, you will protect from encryption. Again, store your keys securely. And then against side channel attacks, you will use electromagnetic shields. And there are also some hardware-based masking algorithms. Now that we have seen potential solutions for your security problems, one might ask, okay, but on my low power, low cost, small size device, I cannot implement all these measures. That will be so expensive, I don't have space. Well, the good news is that maybe it's already enough to have a considerate hardware and firmware design, considering that such low-cost devices usually come in great redundancy. You won't deploy only one temperature sensor. You will have a whole fleet, so if you lose one of your devices, that won't be the end of the world. However, now if you think about gateways, they come in a way more, you don't have that kind of redundancy. You might have one gateway for hundreds of devices. There, you actually really need to include a silicon level of protection through a hardware root of trust. Maybe also some additional circuitry, a hardware watchdog, or a voltage supervisor. Then, of course, highly secure devices, they need end-to-end solutions. With that being said, I would like to introduce our Miro Edge Sphere LoRaWAN gateway. This gateway is based on the Microsoft Azure Sphere cloud platform. And the hardware is actually based on the Pluton security subsystem, which implements many of these functions that we talked about today. If we have a look at how this integrates into the LoRaWAN ecosystem, as you can see, the Azure Sphere platform does not connect in any way to the LNS. That basically also means you are not tied to a specific LNS. On the other hand, the Azure Sphere platform, it acts like a guardian. It protects your gateway from being attacked. The take-home message from here is your gateway is the point where you should protect because that's basically the road where all the traffic goes through. With that, I would like to conclude my presentation. Thank you so much for your attention, and make sure to visit us at IoT Visions, which will take place in Zurich next summer.